My name is Gamil. I am from New York University in Abu Dhabi, and in this presentation I would like to introduce Muon-Ra, a quantum random number generation method from cosmic rays.
First off, I would like to motivate our work by bringing up a vulnerability that appeared in 2008. So researchers discovered that the Debian distribution was producing predictable SSH key pairs, and specifically the issue came from the fact that OpenSSL utilized a pseudo-random number generator for its operations. The main problem is that pseudo-random number generators are deterministic, which makes them problematic in cryptographic applications. In this case, the programs always started from the same state, which is an all-zero state, and as you can imagine, this allowed the attackers to track the evolution of the entropy pool and eventually predict secret keys. More specifically, the attackers were able to predict the master key in the RSA mode, while for the DHE mode, the attackers were able to predict the client's Diffie-Hellman private key. As you understand from this event, this is why pseudo-random number generators are not effective in modern cryptographic applications, and this is why we require an RNG that produces non-deterministic sequences of numbers. This is where true random number generators come in handy. True RNGs are methods that utilize entropy that is gathered from physical phenomena, which is exactly what makes these solutions non-deterministic. Multiple TRNGs have been developed so far. However, these current solutions exhibit several issues that make them ineffective for commercial and embedded applications. The main reason for that is that most solutions utilize an active entropy source, meaning that they gather the required entropy from a device, for example, lasers. And while this might be effective in acquiring high random number generation rates, it also causes several issues. The main issue is that the power consumption of the RNG will be significantly increased since the solution is utilizing an additional device for its operation. And also, in several cases, these devices occupy a lot of space and generate significant amounts of heat, which means that they cannot be active for long periods of time. So as you can imagine, such solutions cannot be utilized for commercial or embedded applications, and this is why we need a true random number generator that can be easily integrated in devices. To solve the issues that I mentioned previously, we designed the first secure RNG that utilizes muons. More specifically, this solution makes use of a muon tracking system as a harvesting mechanism that passively records the time of crossing muons to produce a stream of random bits. The proposed implementation has the capability to be reduced down to chip size and be integrated in modern systems. And the main points are that we introduce a new low-power harvesting mechanism for true random number generation, and that we test the proposed design using two well-established randomness evaluation mechanisms to verify its randomness. So moving on, I would like to present the preliminaries and give some important information about random number generators and their categories. So RNGs can be categorized as either pseudo RNGs or true RNGs. Pseudo RNGs are based on computer-based deterministic algorithms or mathematical formulas, and therefore they produce a zero-biased periodic sequence of numbers. Even though several pseudo RNGs pass well-known statistical tests, they exhibit a high rate of determinism, and this is why they are unreliable for applications in cryptography, as we saw earlier. Unlike pseudo RNGs, true RNGs rely on randomness of physical phenomena and processes that are characteristically stochastic and non-deterministic. Most true RNGs can be further categorized into three distinct families based on the source of randomness. So we have noise-based RNGs, free-running oscillator or FRO RNGs, and quantum RNGs or QRNGs. To briefly describe each category, noise-based RNGs depend on white noise amplification to generate random numbers. FRO RNGs utilize the timing jitter of their oscillators to produce an output, while for quantum random number generators, they exploit quantum effects of the environment to generate the stream of random bits. Since our proposed solution can also be categorized as quantum RNG, I would like to focus a little bit more in this section. But before I do that, I would like to talk a little bit about the components of true random number generators. So it is important to mention that true RNGs consist of two major components, an entropy source and the harvesting mechanism. An entropy source can be defined as the place from which randomness is gathered, and such sources range from physical randomness, derived from concepts such as quantum mechanics, nuclear decay, and thermal noise, to more simplified concepts like the movement of a mouse. More specifically, sources of an entropy can be further categorized to active or passive, designating the existence or the absence of a device for the process of sourcing entropy. Active sources range from resistors to photonic lasers and oscillators, while passive sources are considered concepts available in the environment that can be measured, and this can be atmospheric noise and radioactive elements. The second component is the harvesting mechanisms, and it's the component that is utilized to extract the entropy from its source. In this case, one example that we can mention is the photon detectors, which are used to capture photons. Now I want to move back and present some of the existing work that has been published regarding quantum random number generators. And specifically, I want to focus on three different directions that these solutions aim to improve, which are bias-free focused designs, performance-focused designs, and low-power focused designs. In this slide, I would like to present two works that focus in bias-free solutions. The first study is based on the arrival time of photons and attempts to eliminate bias and autocorrelation, and eventually manages to reach very low levels of bias. The second study provides a solution that is based on the arrival time of photons and their wave function, and manages to not require any post-processing operations at all. As you can see from the schematic of the second solution, this QRNG utilizes a laser and an avalanche photodiode to produce results. It is important to mention that the avalanche photodiode is operating at a voltage of 45.9 volts, and as you understand, the utilization of such components consume significant amounts of power, and therefore this makes them inefficient for embedded applications. So regarding high-speed RNGs, one of the most frequently used solutions is the use of a beam splitter. This component is capable of changing the direction of moving photons in a vertical or horizontal manner, and therefore it creates two random outcomes. The first work that we describe here utilizes this method and manages to reach RNG speeds that exceed 100 megabits per second. Next, we have one solution that is based on a similar concept, and it makes use of the arrival time of cosmic photons that are generated from a light-emitting diode. This solution manages to reach a random number generation rate of 152 megabits per second. Lastly, a more complex state-of-the-art implementation is based on the measurement of quantum phase noise of a single-mode laser. This solution relies on random phase fluctuation in an electric field to generate random numbers, and they manage to produce a generation rate of 500 megabits per second. So as you understand from these three solutions, they exhibit high random number generation rates. However, this comes at the cost of utilizing an active entropy source. In this case, they all use lasers. And as we explained earlier, this is problematic for multiple reasons. While all the previously mentioned solutions present interesting results, none of them focus on minimizing the power consumption of their solution. The closest solution to our work is a true RNG mechanism with low power properties, and it's based on Homodyne detection. Homodyne detection means that the solution is extracting information from an oscillating signal by comparing that signal with a standard unmodified oscillation. In this case, the solution is utilizing a bright laser that acts as an oscillator to measure the field's interference. And while this solution requires only 4.5 milliwatts of power, it still depends on an active source of entropy, in this case the bright laser, which translates to additional power consumption and excessive levels of heat and area for the design. So, as we have seen so far, most implementations are comprised of an active entropy source, which is something that oftentimes limits their applicability. Combining their considerable dimensions with the power consumption and the cost oftentimes make designs utilizing active entropy sources an undesirable solution, for example, in the cases of embedded devices. To counter this issue, we wanted to find a solution that would be beneficial for embedded devices, and this is why we investigated further on passive sources of entropy. What we realized from our exploration was that most solutions were utilizing photons as a source of entropy. In addition, we found that photons can be easily generated by humans through lasers, which could be dangerous for cryptographic applications. That is why we specifically investigated for particles that are hard to tamper with. So we found out that a good candidate for this would be muons. And the reason for that is that the only way that humans can generate this particle is through a particle accelerator. This means that if someone wanted to tamper with a muon detection mechanism, they would have to have access to such a device to make it possible, which is highly unlikely. So the fact that muons are hard to tamper with in combination with their high generation rates and their non-deterministic trajectories is what motivated us to use muons as a source of entropy for our mechanism.
Now I would like to briefly describe the methodology behind Muon-Ra. So our QRNG design can be observed in the schematic, and as you can see, we section this design in three different parts: those of the physical domain, the analog circuit, and the digital circuit. So the process begins with the muons passing through the scintillators. This causes them to emit light, which is then captured by the silicon photomultipliers. The detection of light emissions by the silicon photomultipliers generates an analog pulse, which is sent to the signal processor and eventually allows the tracking of information on the passage of charged particles. From this point, once the signal coming from the detector is identified by the signal processor, the RNG starts to accumulate entropy and stores it in a buffer. Once enough entropy has been accumulated, the post-processing stage is initiated to eliminate bias. This, in other words, means that the gathered entropy has to go through a hash function. The output of the hash function is eventually stored in a final buffer, which contains all the true random numbers generated by our design. So in order to evaluate our quantum random number generator, we had to use a muon tracking system. The muon tracking system used for our design uses multiple plastic scintillator bars that contain a wavelength shifter fiber, which is connected to a silicon photomultiplier. Silicon photomultipliers are compact photosensors with an active detection area of about 1 millimeter squared. So the way they work is that when muons pass through the scintillator bars, they cause them to emit light, which is then captured by the silicon photomultipliers, and wavelength shifter fibers are used to collect and shift the scintillation light to avoid self-reabsorption. As I mentioned previously, the detection of light emissions by the silicon photomultipliers is what generates an analog pulse, which eventually allows us to record information about those particles. Customized electronics have also been installed to read out the silicon photomultipliers, along with control of the working parameters and the ability to generate the trigger logic pattern. And eventually what happens is that when a muon passes through the detection mechanism, the time of the crossing is recorded and transferred to a computer device in real time.
In this slide, I want to talk a little bit about how we collect entropy for our system. I previously mentioned the way we obtain entropy is through measuring the time intervals between muons detected by our tracking system. But I think it's important to talk a little bit about this process in more detail. So the process of generating time intervals begins once the signal coming from the detector is identified by the quantum RNG. When this happens, our system initiates a time counter, and when a second muon is detected, a new signal is generated and transmitted to the QRNG. At this point, our random number generator records the time interval between the first and the second muon strikes and stores the result on a buffer, which accumulates our entropy. At the same time, the value of the counter resets and the process repeats. It is important to note that the proposed implementation will not produce random values when muons are not detected. So if someone blocks the randomness source, our RNG will not produce any deterministic values. So this process occurs multiple times until enough entropy has been accumulated in the buffer. And once the buffer has sufficient entropy, the values undergo a modification process to remove any biases. Now, I want to talk about the process of removing biases from the collected entropy, but before I do that, I would like to explain the reason for doing this. So in order to ensure an accurate quantum random number generator, we need to address two concerns. First, we need to address the non-flat distribution of random intervals between muon strikes, and this is something you can see from the graph that appears in this slide. And secondly, we also need to address the noise that is propagating from the analog to the digital domain through the utilized muon tracking system. So as a result, it is necessary to ensure that the distribution of the extracted bits is uniform, and therefore this is why we introduce a hashing process. So to correct for this bias, we use the SHA-1 hash function, and we denote the positive integer that describes the number of time intervals with n, and the length of each time interval in bits with b. hi is our input to the hash function, and since the length of hi is relatively large, it is required to concatenate n time intervals such that n times b is equal to the input to our hash function. The final step is to perform the hash function, and this happens by feeding hi biased bits as input and getting ho unbiased bits as output. In our case, we pass an input of 168 bits through SHA-1, and we generate 160 unbiased bits as an output. And the reason for choosing this number of 168 bits is because it allowed us to maximize our random number generation rate while we still produced random results. Now I would like to talk a little bit about the conditions of our experiment. During our experiment, the tracking system was positioned near sea level and operated at 300 MHz. So under these conditions, the muon tracking device exhibited detection rates of about 20 muons per second, and from each muon strike, we were able to produce 28 bits of information. This means that about 576 bits were generated each second before going through the post-processing phase. For the evaluation of our proposed quantum random number generator, we wanted to assess our system based on 3 different categories, and these were performance, randomness, and power consumption. Regarding its performance, after applying the post-processing phase, we were able to reach a random number generation rate of 549 bits per second. As you can see from this slide, this is a low number compared to a state-of-the-art solution, which manages to reach a random number generation rate of up to 1.2 gigabits per second. The reason for this is the fact that we are using a passive entropy source, while the state-of-the-art solution is utilizing an active one. However, as we described previously, there are many limitations that come with this and make the solution inefficient and ineffective for embedded applications. Moving on, I would like to talk a little bit about the way we evaluate our solution regarding its randomness. So in this experiment, we assess the quality of random numbers of our design using 2 standard randomness evaluations. These 2 evaluations were the NIST statistical test suite and the die-harder battery of tests. So the NIST STS is considered one of the most important testing suites for randomness analysis. It was published as a NIST standard in 2010, and it is the first step in assessing the suitability of RNGs for cryptographic applications. The statistical test suite is comprised of 15 evaluations that are defined by very complex computations, and therefore they prove to be very difficult to pass, even for genuinely random information. The tests either evaluate the randomness of the sample per bit or per blocks of bits. And this is why we can categorize these evaluations in 3 different groups. And these groups are made according to the type of statistic test and the size of the analyzed sequences. So we have bits, which analyze the randomness of the sample per bit. We have m-bit blocks that assess the randomness of the sample in blocks of m-bit length, where m is smaller than 30 bits. And we have big M bit parts, which evaluate the randomness of the sample in parts of big M bit length, where big M is greater than 1,000 bits. Die-harder is also another random number generator testing suite. It is defined as a compilation of multiple well-established RNG evaluations, including those of die-hard, the NIST STS, and RGB. To elaborate a little bit more, die-harder contains improved tests developed on die-hard and a limited set of tests that is derived from the NIST statistical test suite. Lastly, the die-harder testing suite also contains less known evaluations that were discovered from literature or it was provided by users. In this slide, we provide the results of the NIST STS and the die-harder evaluations. As you can see from the results illustrated in these tables, the proposed method is successful in passing all randomness tests in both the NIST STS and the die-harder evaluations, and therefore it proves its effectiveness in generating truly random numbers, which demonstrate its suitability for cryptographic applications. It is important to mention that regarding the NIST STS, the tests are considered a pass when they obtain a score that is above 0.05%. And in die-harder, the tests are considered a pass with scores above 0.05% and below 99.5%. Lastly, I would like to say a few words about how we evaluated our mechanism regarding its power consumption. So, as we saw from our evaluations, the power consumption of the digital circuit can be significantly reduced when implemented in global foundries, specifically on 65 nanometers CMOS, at an operating voltage of 1.2 volts. What we identified is that the debiasing circuitry, when realized using the SHA-256 hash function, consumes around 20 microwatts, and that regarding the analog signal conditioning, the circuit can be as simple as a CMOS inverter-based amplifier, meaning that its output can be fed as a clock to a D flip-flop for detection. In this case, the power consumption of an inverter and a D flip-flop will be less than 10 microwatts, and since the chip implementation already requires a detector and the SHA-256 hash function to operate, the power consumption can be reduced down to 30 microwatts. So as you can see, our mechanism significantly reduces the power consumption compared to other state-of-the-art solutions. And more specifically, Muon-Ra consumes about 150 times less power compared to the solution that was described previously. To conclude, the target of this work was to explore a true random number generator that could be embedded in a low-power device. And as a solution to that, we have proposed and evaluated the first quantum random number generator based on muons. The proposed implementation makes use of a muon tracking system as a passive entropy source, with the potential to be reduced down to chip scale. The implementation is capable of reaching a random number generation rate of up to 549 bits per second, with a power consumption of about 30 microwatts, making it ideal for low-power embedded applications. To the best of our knowledge, this is the first solution that utilizes muons to produce random numbers, and the proposed architecture is successful in passing all the NIST STS and the die-harder tests, which is something that makes it ideal for cryptographic applications. With this, I would like to conclude my presentation on Muon-Ra, a quantum random number generation method from cosmic rays. I hope you enjoyed it, and thank you very much for listening.